A water pumping station grounding system should achieve a grounding system resistance of 5 ohms or less. This involves several components. Firstly, a ground ring, which is a continuous loop of bare copper conductor encircling the perimeter of the station. Secondly, ground rods, which are multiple copper-clad rods driven into the earth. And thirdly, a lin-coat chemical ground rod, which enhances grounding in difficult soil conditions. And fourthly, a Ufer ground, which utilizes the steel reinforcing bars within the concrete foundation of the station building. For the ground ring, use a minimum of #4 American wire gauge bare copper conductor. Install the ring at a depth of 24 inches below grade. Connect the ground ring to all grounding components. For the ground rods, use 3/4 inch diameter x 10-foot long copper clad rods. Drive the rods into the earth at least 8 feet deep. Space the rods approximately 20 feet apart. For the lin-coat chemical ground rod, install the rod according to the manufacturer's specifications. Connect the rod to the ground ring and ground rods. For the Ufer ground, identify all exposed steel reinforcing bars in the concrete foundation. Clean the bars to remove any paint or coating. Weld a copper bonding strap to the reinforcing bars. Connect the bonding strap to the ground ring. After installation, ground resistance measurements should be taken using a ground resistance tester to measure the resistance between the ground ring and a remote earth ground reference point. The measured resistance should be 5 ohms or less. Perform a visual inspection to ensure all connections are tight and secure. Inspect the ground ring for any breaks or damage. Verify the integrity of the lin-coat chemical ground rod. Maintenance is essential. Inspect the grounding system annually for signs of corrosion or damage. Perform ground resistance testing regularly to ensure compliance with the specified value. Make necessary repairs or upgrades as needed to maintain the system's effectiveness. By following these guidelines, it is possible to achieve a grounding system that meets the specified resistance of 5 ohms or less, ensuring the safety and proper operation of the water pumping station. The ground ring serves as the backbone of the grounding system, providing a low impedance path for fault currents to return to the source. The #4 American wire gauge copper conductor provides ample cross-sectional area to handle these currents. Burying the ring at a depth of 24 inches helps to ensure that it is in contact with moist soil, which improves its conductivity. Connecting the ground ring to all other grounding components ensures that all parts of the system are electrically bonded together. Ground rods provide additional paths for fault currents to dissipate into the earth. The 3/4 inch diameter and 10-foot length of the rods provide a large surface area for contact with the soil. Driving the rods at least 8 feet deep ensures that they are in contact with moist soil. Spacing the rods approximately 20 feet apart helps to minimize the overlap of their spheres of influence, which improves their effectiveness. Lin-coat chemical ground rods are designed to improve grounding in areas with poor soil conductivity. These rods contain a chemical compound that leaches into the surrounding soil, increasing its conductivity. It is important to install these rods according to the manufacturer's instructions to ensure that they function properly. Ufer grounds utilize the existing steel reinforcing bars in the concrete foundation of a building as part of the grounding system. Concrete is a relatively good conductor of electricity, and the steel reinforcing bars provide a large surface area for contact with the soil. To create a Ufer ground, the reinforcing bars must be electrically bonded together and connected to the ground ring. This is typically done by welding a copper bonding strap to the reinforcing bars. Testing and verification are essential to ensure that the grounding system is functioning properly. Ground resistance testing should be performed using a 3-point fall of potential method. This method involves driving 2 auxiliary ground rods into the earth at a distance from the ground ring. A ground resistance tester is then used to measure the resistance between the ground ring and the auxiliary ground rods. The measured resistance should be 5 ohms or less. Visual inspection should be performed regularly to check for any signs of corrosion or damage to the grounding system. Any damaged components should be repaired or replaced immediately. Maintenance is critical to ensuring the long-term effectiveness of the grounding system. Ground resistance testing should be performed annually to ensure that the system is still meeting the required resistance. Any necessary repairs or upgrades should be made promptly. Additional details of ground ring installation include ensuring proper exothermic wells or compression connectors are used for all connections to maintain conductivity and prevent corrosion. Also consider the soil composition when determining ground rod placement, as soil resistivity can vary significantly even within a small area. If high soil resistivity is encountered, additional ground rods or chemical ground rods may be required to achieve the desired resistance. The Linkert chemical ground rod requires periodic maintenance to ensure the chemical continues to leach into the surrounding soil. Follow the manufacturer's recommendations for replenishment or replacement of the chemical compound. When connecting to the Ufer ground, ensure that the concrete is clean and free of any coatings that could impede electrical conductivity. The welding of the copper bonding strap to the reinforcing bar should be performed by a qualified welder to ensure a strong and reliable connection. Regular ground resistance testing should be performed at different times of the year, as soil moisture levels can affect the resistance of the grounding system. Testing during dry periods will provide a worst-case scenario reading. All testing should be documented, and records should be kept for future reference. Furthermore, ensure the grounding system is bonded to all metallic components within the pumping station, including pipes, equipment frames, and enclosures. This bonding helps to minimize voltage differences and reduce the risk of electrical shock. The size of the bonding conductors should be selected based on the size of the equipment grounding conductors, in accordance with applicable electrical codes. Consider using corrosion-resistant materials for all grounding components, especially in areas with high soil salinity or corrosive chemicals. Stainless steel or copper-clad steel ground rods can provide improved corrosion resistance compared to standard copper-clad rods. If the water pumping station is located in an area with a high lightning strike frequency, consider installing a lightning protection system in addition to the grounding system. The lightning protection system should be designed to intercept lightning strikes and safely conduct the current to ground. The grounding system should be integrated with the lightning protection system to provide a common ground reference. It is important to consult with a qualified electrical engineer to design and install the grounding system for the water pumping station. The engineer can assess the specific site conditions and requirements and recommend the appropriate grounding system components and installation methods. The grounding system should be inspected and tested by a qualified electrician after installation to ensure that it meets all applicable codes and standards. Regular inspections and testing should be performed throughout the life of the pumping station to ensure that the grounding system continues to function properly. Finally, proper documentation of the grounding system is essential for future maintenance and troubleshooting. The documentation should include a detailed plan of the grounding system, including the location of all grounding components, the size and type of conductors, and the results of ground resistance tests. The documentation should be kept in a safe and accessible location. Implementing these guidelines and best practices will help to ensure a safe and reliable grounding system for the water pumping station, protecting personnel and equipment from electrical hazards. Remember that local and national electrical codes must be followed. A key consideration in grounding system design is soil resistivity, which can vary significantly depending on soil type, moisture content, and temperature. High soil resistivity increases the resistance of the grounding system, making it more difficult to achieve the desired 5 ohms or less. Several methods can be used to reduce soil resistivity, including chemical treatment, ground enhancement materials, and the installation of additional ground rods. Chemical treatment involves adding chemicals to the soil to increase its conductivity. However, this method can be environmentally harmful and may not be permitted in some areas. Ground enhancement materials are conductive materials that are buried in the soil to improve its conductivity. These materials are typically made of a mixture of carbon, bentonite clay, and other additives. The installation of additional ground rods is a simple and effective way to reduce soil resistivity. The more ground rods that are installed, the lower the overall resistance of the grounding system. Another important consideration is the bonding of all metallic components within the water pumping station. This includes pipes, equipment frames, enclosures, and other metallic objects. Bonding helps to minimize voltage differences between these components, reducing the risk of electrical shock. Bonding conductors should be sized according to applicable electrical codes and should be securely connected to all metallic components. The use of exothermic welding is recommended for making bonding connections, as it provides a strong and reliable connection that is resistant to corrosion. Surge protection devices should be installed at the service entrance of the water pumping station to protect against voltage surges caused by lightning strikes or other events. Surge protection devices divert surge currents to ground, preventing them from damaging sensitive equipment. The grounding system should be properly coordinated with the surge protection devices to ensure that they function effectively. Regular inspections of the grounding system should include checking the condition of all grounding conductors, connections, and ground rods. Any corroded or damaged component should be replaced immediately. Ground resistance testing should be performed annually to verify that the grounding system is still meeting the required resistance. If the resistance is higher than 5 ohms, correct action should be taken to reduce the resistance. These actions may include adding additional ground rods, treating the soil, or replacing corroded components. The documentation of the grounding system should be updated whenever any changes are made to the system. This includes adding new ground rods, replacing components, or performing maintenance. Accurate documentation is essential for ensuring the long-term reliability and safety of the grounding system. Finally, it is important to remember that the grounding system is only one part of a comprehensive electrical safety program. Other important elements of an electrical safety program include proper training, the use of personal protective equipment, and the implementation of lockout/tagout procedures. By following these guidelines and best practices, you can help to ensure a safe and reliable electrical system for the water pumping station. The grounding system's effectiveness is also tied to the local geology. A geological survey might reveal subsurface conditions that hinder grounding, such as rock layers or dry sand pockets. In such cases, deeper ground rods or specialized grounding electrodes may be required. The depth of the water table is another crucial factor. Ground rods that extend into the water table generally provide lower resistance. However, the water table level can fluctuate seasonally, so the grounding system should be designed to maintain adequate performance even during dry periods. The type of soil is also important. Clay soils generally have lower resistivity than sandy soils. However, the resistivity of clay soils can vary significantly depending on their moisture content. Sandy soils tend to have more consistent resistivity, but it is generally higher than that of clay soils. The presence of chemicals in the soil can also affect its resistivity. For example, soils that are contaminated with salt or other conductive chemicals will have lower resistivity than soils that are free of contaminants. The local climate can also play a role. In areas with high rainfall, the soil will generally be more moist and conductive. In areas with low rainfall, the soil will be drier and less conductive. The grounding system should be designed to take into account the local climate and soil conditions. The use of ground-enhancing compounds can be helpful in areas with poor soil conditions. These compounds are designed to improve the conductivity of the soil around the ground rods. There are many different types of ground-enhancing compounds available, so it is important to choose one that is appropriate for the specific soil conditions. Another option is to use a chemical ground rod. Chemical ground rods contain a chemical compound that leaches into the surrounding soil, improving its conductivity. Chemical ground rods are typically more expensive than standard ground rods, but they can be very effective in areas with poor soil conditions. The use of a Ufer ground is another good option, especially if the water pumping station has a concrete foundation. A Ufer ground consists of the steel reinforcing bars in the concrete foundation, which are connected to the grounding system. Ufer grounds can provide a very low resistance ground, especially in areas with poor soil conditions. The design of the grounding system should also take into account the potential for lightning strikes. If the water pumping station is located in an area with a high lightning strike frequency, it is important to install a lightning protection system. The lightning protection system should be designed to intercept lightning strikes and safely conduct the current to ground. The grounding system should be connected to the lightning protection system to provide a common ground reference. The design of the grounding system should also take into account the potential for stray currents. Stray currents are currents that flow through the earth due to electrical imbalances. Stray currents can cause corrosion of underground pipes and other metallic structures. The grounding system should be designed to minimize the flow of stray currents. The grounding system should also be inspected regularly for damage. Damage to the grounding system can reduce its effectiveness and increase the risk of electrical shock. Any damaged component should be repaired or replaced as soon as possible. The grounding system should also be tested regularly to ensure that it is still providing adequate protection. The ground resistance should be measured at least once a year. If the ground resistance is too high, corrective action should be taken to reduce it. The grounding system is an essential part of the electrical system of the water pumping station. A properly designed and maintained grounding system can help to protect personnel and equipment from electrical shock and damage.